which monomer is best able to undergo cationic polymerization. So all of our monomer options are substituted ethylene units. So we are looking at a chain growth polymerization. So we're taking our monomer unit, we'll be reacting it to make a reactive intermediate, and then that reactive intermediate will react with another unit of the alkene. So let's take a look at what this would look like for a cationic polymerization, get an idea of what that reactive intermediate looks like, and that will allow us to select which of these substituents on the alkene is going to work best. So if you're looking at a substituted ethylene, which would be what we start with for a chain growth polymerization. And if we're making a cation, most likely we're going to be protonating this alkene. So I'm going to add in a proton source. And we know how alkenes react with protons. Now we're going to add this hydrogen. That hydrogen will go to the less substituted carbon atom of the chain in order to give you the more substituted and more stable cation intermediate. So we would have, in this case, a CH3. And we're going to have a positive charge right here. And so this can react with another unit of the monomer. And this is how we'll make this chain growth polymer through a cationic polymerization. So we've got a cation and we've got an alkene that can be an anion, a nucleophile. I'm sorry, not an anion, a nucleophile. And so that can react with our cation. So this is how we're growing the chain, and it's going to give us a new reactive intermediate, a new cation on this carbon right here. So there was our initial monomer unit. It is now neutral because we now have 4 bonds on that carbon, and now it's bonded to this next CH2 group. And this carbon atom here is going to be left without a full octet, so now that's going to be our cation. And this chain can continue growing. So to be able to undergo a cationic polymerization, this just means you want your X group should be able to stabilize the catalyst, or sorry, not the catalyst, the cation. And so what that really means is that we're looking for X to be an electron donating group. So for a cationic polymerization, we want this to be electron donating. So if we take a look at our options, we know from previous studies that a carbonyl is electron withdrawing. We can pull those electrons out. We get to B here, we've got lone pairs of electrons on the oxygen. This is an electron donating group that can push electrons into your alkene. Right here, you've got an electron withdrawing group, so that's not going to work as readily. This nitro group's a pretty powerful electron withdrawing group because we could actually pull those electrons all the way out into the nitro group. And here you've got in D something similar to what you have in A, where that's electron withdrawing. So our monomer that has the electron donating group is going to be the best for a cationic polymerization.